Welcome back to the Deep Dive. Today we are tackling one of the really fascinating but also quite daunting challenges in modern AI. We're talking about creating truly smart robots. Robots that can safely navigate and, actually assist us in the real world, the messy, dynamic real world.
Yeah, it's a huge step up.
We're definitely moving beyond those simple pre-programmed tasks you see on like a factory floor. We're diving into the complexity of, say, your own home. It's cluttered, people move unpredictably, safety is just paramount.
That's exactly right. Our mission today is really an in-depth look at these things called multi-agent robotic systems, or MARS, and also the critical tech underneath them. Vision language action models, VLA models.
VLA, okay.
Because the existing systems, they really struggle with, well, a few core things. Risk-aware planning is one, getting genuine user personalization is another, and maybe the toughest, translating our, often vague human language into safe, executable robot skills, especially in places built for people, not robots.
Right, cluttered indoor environments. And the key takeaway from the research we looked at, it seems, isn't just about building a single, smarter robot brain.
No, not monolithic.
It's more about shifting to a collaborative system, like a distributed intelligence, where these specialized agents work together.
Constantly checking, correcting each other, yeah.
To make sure safety and personalization are always, like, the top priority.
That's the goal.
Okay, so let's unpack that specialized system first. MARS, you called it. Multi-Agent Robotic System.
The one.
And it's powered by these multimodal large language models, MLLMs, designed specifically for smart home robots, often assisting people, maybe those with mobility challenges.
Exactly. Assistive tech is a key driver here.
So what are the collaboration bits, the mechanisms that make this whole thing genuinely risk-aware?
Well, MARS works as this four-stage kind of closed-loop workflow. It uses four tightly integrated agents. And that integration is what gives it robustness, in environments that are constantly changing. It all kicks off with the visual perception agent.
Okay, so that sounds like the eyes of the operation.
Precisely. This agent uses pretty advanced models, often MLLMs combined with other things like CLIP. It processes high-res images, depth information. Basically, it extracts semantic features, what things are, and spatial features, where they are.
So it recognizes objects, but also measures things like how wide a doorway is, or how tall an obstacle might be compared to, say, a wheelchair.
Exactly that level of detail. It doesn't just see couch, it sees couch blocking 60% of the main pathway.
Ah, okay. Much more useful.
Right, and that rich data stream then flows into the second agent, the risk assessment agent.
Okay, hazard identification.
Yes, and importantly, it's not just AI guessing. It combines that MLLM's semantic reasoning, understanding the meaning of the scene, with predefined human safety rules.
Like actual standards.
Yeah, like minimum width thresholds for safe wheelchair passage, things like that. It then assigns severity scores, urgency scores, to risks like narrow gaps, cluttered floors, maybe something blocking an emergency exit.
And what comes out of that assessment? What can the robot do with that?
Those prioritized risks feed straight into agent number 3, the planning agent. This agent takes the high-risk items identified and generates an actual executable action sequence.
A plan.
A plan, yeah. But it's optimized not just for, getting the job done quickly. It's optimized for risk mitigation.
So the plan might be a physical action, like moving something.
It could be, like moving a laundry basket that's in the way. Or it could generate path guidance that steers the user around a wet patch on the floor.
And finally, there's some kind of check, an oversight layer.
That's the fourth agent.
Okay.
The evaluation agent. This is really crucial. It's where iterative optimization happens. Before anything gets executed, this agent checks the plan. Is it feasible? Is it safe? And it does this across 4 critical dimensions.
Okay, hold on. 4 dimensions. You're saying it's not just checking, will this plan work, or is it fast enough? It's being scored on. Assistance user experience, and even ethical and social alignment.
That's right.
That feels like a massive shift from just typical robot path planning. What does ethical alignment even mean for a robot's plan?
It means the system is actively trying to avoid plans that, might be technically efficient, but could be socially awkward, or maybe cause unnecessary stress for the user, or even violate their privacy settings.
Wow.
So, if the evaluation agent flags a potential issue in any of those areas, UX, ethics, safety, feasibility, it kicks feedback immediately back to the planning agent.
Make adjustments.
Exactly. Adjust the plan. It ensures the robot's behavior feels right. aligns with human comfort and expectations, not just hitting the technical targets.
Okay, here's a concrete example for you, the listener, just to make this real. That risk classification in Mars, it's very specific. A high risk, needing immediate attention, isn't just like some clutter. It's defined as something like a chair completely blocking the main doorway, no other way around.
Right, a critical blockade.
Or, say, a wet, slippery patch of floor directly on the planned route. The system is trained to assess immediate harm, the urgency, based on how close it is to the user and their specific needs.
And that detail really underlines the closed-loop workflow, right? Perception, risk analysis, planning, then that iterative evaluation and optimization. And the final output, importantly, isn't always just robot commands. It might include alerts or guidance for the user, maybe for a caregiver. It keeps that human connection, that transparency.
Okay, that Mars system sounds incredibly thought through, but it relies on this foundational tech, right? Let's switch gears to that. The vision language action models, the VLAs. Why did AI need this evolution? Why move past systems handling vision and language separately? What was this integration gap you mentioned?
Well, historically, AI systems were really fragmented. You had brilliant computer vision models. CNN's great at spotting things. You had large language models, LLMs, fantastic in understanding instructions. And then you had totally separate policy networks to control the robot's physical actions.
Right, different specialists.
Exactly. But linking them up was the nightmare. You tell a robot, pick up the red block, vision finds it, great. But then maybe the block shifts a tiny bit, and the action policy just fails. Because the connection, the translation between what the vision system saw, what the motion system needed to do, was often manual, brittle, hard-coded.
So the different parts couldn't really speak the same language, operationally speaking.
Precisely. They were siloed, great in their own domain, but putting it all together for fluid, adaptable behavior. That was the struggle. It led to systems that were brittle, didn't generalize well. You had to retrain massively for even tiny changes in the task.
So the big leap with VLA is this unification. If the goal is that fluidity, how do these models actually manage it? How do they encode everything? Sight, instructions, the robot's own state, the actions into these, you said, language-like tokens.
They essentially create a shared vocabulary, a unified embedding space.
Wow.
Everything gets turned into discrete tokens, conceptually like words in a sentence.
Okay.
And the model processes these tokens autoregressively, one after another. There are roughly 4 main types of tokens working together here. First, you've got language tokens. They encode the instruction you give it, like open the blue cabinet, grab the towel.
Standard LLM stuff. Then the vision.
Second, vision tokens. These encode the visual stream. Using vision encoders like VIP maybe, it segments the scene, classifies objects, the cabinet, the towel, other things around them, their positions relative to each other.
Okay, sight and instruction. But the robot needs to know about itself, right? Where its arm is right now, how fast its wheels are turning. How does that get into the mix?
Critical point. That's the third type. State tokens. These are absolutely crucial. They encode the robot's real-time physical status, its proprioception, joint angles, force feedback from its sensors, maybe LiDAR depth readings.
Okay.
And these state tokens let the model reason dynamically about physical constraints. Like, okay, I need to reach for the towel, but there's a fragile vest nearby. I need to adjust my arm path slightly to avoid hitting it.
That's sophisticated. And then the output, the actual movement.
That's the fourth type, action tokens. These are generated by the model autoregressively based on all the input tokens, the language, the vision, the state. These action tokens represent the low-level motor commands, like precise updates to joint velocities or steering commands for the wheels. The whole sequence turns the VLA into this incredibly sophisticated, language-driven policy generator.
So it really is like the robot is generating a sentence of motion, token by token, action by action, based on sight and language. That unified process, yeah, that feels like a paradigm shift.
It really is. And that unified approach, it spurred a lot of rapid innovation in architectures, things that improve safety, improve performance. We're seeing stuff like dual system architectures. NVIDIA's Groot N1 is an example.
How does that work?
It basically combines 2 systems, a fast, low latency system for the actual execution, the fine motor control, and alongside it, a slower, more deliberate LLM-based planner that handles the complex, high-level thinking, the task decomposition.
So you get the best of both worlds, strategic depth and real-time speed.
Kind of, yeah. The strategic thinking of the LLM combined with the reflexes needed for physical control.
And what about when things inevitably go wrong? Robots operating in messy homes are going to fail sometimes.
Absolutely, and that's where self-correcting frameworks come in, like SCVLA. These are really clever. They have a default fast path for actions, quick, efficient. But if something goes wrong, maybe the robot drops something or a grasp fails, it immediately triggers a slow correction path.
Okay, what happens though?
This slow path uses LLM-based chain of thought reasoning. It tries to diagnose why the failure happened. Did I grip too hard? Was the object slippery? And then it suggests a recovery strategy.
And does it work?
The research showed it reduced task failure rates by something like 35% in complex tasks, which is huge.
35%. Yeah, that's massive in a home setting. It's the difference between the robot just stopping, frustrated, and it actually recovering smoothly and safely. Okay, let's broaden out. Application scope. The power of VLA, this unified language space. It means these systems aren't just for one type of robot, right? The skills can transfer.
That's one of the most exciting aspects. The same underlying tech is handling tasks in wildly different industries. It's genuinely impressive.
Give us some examples.
Okay, so in humanoid robotics, you've got systems like Helix. They're achieving incredibly high control frequencies like 200 hertz.
200 times a second.
Yeah, that enables really fluid, full-body control. And they're showing impressive zero-shot generalization, doing tasks they weren't explicitly trained for in complex domestic settings. Fluidity is key there.
Okay, what else? Cars.
Autonomous vehicles.
Yeah.
AVs, definitely. VLA models are now fusing everything. 2D camera views, 3D LiDAR streams, and language instructions, like take the second right turn after you pass the gas station. Systems like OpenVLA use this unified architecture. The goal is more transparent, more adaptive driving decisions.
High stakes there. Even higher stakes maybe in medicine.
For sure. Healthcare and medical robotics. Think surgical assistance. Systems like RoboNurse VLA are enabling accurate real-time surgical tool handover.
Handing tools to the surgeon.
Exactly. And crucially, they're robust, even if they haven't seen that specific tool before, or if the operating room scene changes dynamically. It's moving beyond just remote control into real autonomous assistance.
Wow. Okay, one more, something linking back to the start, the assistive intelligence idea.
Right. Augmented reality navigation. AR VLAs can fuse visual data, say from smart glasses, with language queries from the user.
Like what kind of query?
Maybe, I need to get to gate 22, but I have to avoid stairs. The VLA processes the visual scene, understands the constraint, avoid stairs, and generates dynamic navigation cues overlaid right onto the user's view.
So it provides accessible, context-aware guidance in complex places, airports, hospitals.
Exactly, personalized navigation support.
That range is incredible. But okay, time for that dose of reality. Despite these amazing breakthroughs, getting VLAs deployed everywhere faces real hurdles: speed, efficiency. What are the main technical roadblocks right now?
Yeah, there are some significant ones. Probably the biggest is real-time inference constraints. The standard way these models generate action tokens, that autoregressive decoding, one token after another, it's just too slow for fluid control.
How slow?
Typically, you're looking at maybe 3 to 5 hertz, 3 to 5 updates per second.
Okay.
But for smooth physical movement, especially in humanoids or assistive bots that interact closely with people, you need way more, like 100 hertz, maybe even higher.
Right. 5 hertz would look very jerky, maybe even unsafe.
It can, yeah.
Yeah.
Even the more advanced parallel decoding methods, they often introduce trade-offs, like making the robot's movements less smooth.
Okay, speed is one. What else?
System integration complexity. There's this fundamental timing mismatch. High-level planning, using those big LLMs to figure out the overall strategy, that can take, 800 milliseconds, maybe more.
Almost a full second.
Yeah. But the low-level motor control, the joints, the wheels, that needs updates really fast, maybe every 10 milliseconds.
Okay, huge difference.
Trying to synchronize those two vastly different timescales, it causes delays, bottlenecks. It contributes to that sometimes jerky, suboptimal movement you see in earlier robots.
And the third big one, hardware.
The sheer size, computational demands. These large VLA models, they need a lot of VRAM, video memory, often more than 28 gigabytes.
Whoa.
And that's way beyond what you can typically pack into the embedded systems, the mobile processors that you need for practical, untethered, battery-powered robots or drones. Putting 28 gigs of VRAM into a small mobile chassis is challenging.
That sounds like a pretty fundamental wall. But you mentioned research is finding ways around these solutions to counter the performance issues, especially around efficiency.
Absolutely. The progress on efficiency is really exciting. One critical technique is low-rank adaptation, or LoRa.
Well, LoRa, what does that do?
It's kind of a game changer for training and fine-tuning. Instead of retraining the entire massive model, which takes huge resources, LoRa injects these small, trainable adapter matrices into the existing frozen layers of the big model. This drastically cuts the number of trainable parameters, maybe by up to 70%, just for the fine-tuning part.
Okay, so it makes it much cheaper and faster to adapt a big pre-trained VLA for a specific new task.
Exactly. It means smaller labs, smaller companies, they can actually afford to customize these powerful models using standard hardware. It really democratizes access.
That helps with the training cost and maybe the VRAM needed for tuning. What about the inference speed? Getting that 3 hertz up to the 100 hertz we need.
Right, the real-time problem. For speed, we're seeing breakthroughs like compressed action tokenization, or FAST.
Fast, what's the trick there?
It basically reformulates how continuous actions like joint movements are represented as tokens. It uses techniques to make the tokens much more concise, often working in the frequency domain. One variant, Pi0 Fast, using this method, achieved a really remarkable 15x faster inference.
15 times faster.
Yeah, and that enabled policy rates of 200 hertz on some high-frequency control tasks.
200 hertz. So that gets us well into the range needed for fluid real-time control.
It does. That 15x speedup isn't just a benchmark number. It's potentially the difference between a robot moving cautiously, hesitantly, around a person, which can feel unnerving, and a robot moving fluidly, intuitively. That builds trust, minimizes risk. It's what could move VLA firmly from the lab into safe, real-world deployment. So, if you step back and look at the big picture, the trend seems really clear. We're seeing this convergence. Powerful VLMs for deep understanding, robust VLA architectures that truly unify vision, language, and action, and these self-correcting agentic AI systems layered on top. It's creating something fundamentally new. These systems don't just perceive and understand anymore. They adapt, they self-correct almost seamlessly, whether it's Mars navigating clutter or SEVLA recovering from a failed grasp.
Yeah, it feels like this whole effort from the Mars risk assessments and those ethical checks to the VLA unified tokens and these huge speed breakthroughs, it isn't just about making faster or smarter robots.
No, the goal seems bigger.
It feels like it's fundamentally about building trustworthy, adaptive agents, agents that can genuinely coexist with us safely. The challenge now, though, it's ensuring these increasingly powerful systems stick to those safety constraints, align with human values in every single decision, every token they predict.
That alignment piece is critical.
So the provocative thought maybe is, what does the future look like when all our devices, from factory arms to personal assistants, are running on these sub-50 millisecond, human-aligned VLA systems? That's definitely a deep dive for another day. Thanks for joining us.
It was a pleasure dissecting the source material with you.